In this video, we'll be examining how to use UCSF Chimera to generate VRML files, or X3D files in this case, for use in Blender and Moldprint 3D. Now, we're also going to make this a more complicated example in which we use a macromolecular structure that we're going to split up into many different parts. And we're going to use a file from the PDB of 1UBQ. This is a ubiquitin molecule here. So it's about 74 amino acids in this case. And the first thing we want to do is not use this ribbon representation. So we can turn this ribbon representation off by clicking hide. And what we want to show is only the atoms and bond representation. In this case, what we're looking at are the bond representation of the molecule, and what we need is the ball and stick representation. And on the GitHub site, there are a number of settings that will automatically set some of these features for us. These are reasonable defaults for use in Chimera. So in this case, I'm just going to copy these. I'm going to go back to Chimera. And I'm going to open in from favorites here, I'm going to open the command line. And down here is our command line. I'm just going to paste all of those commands in there and hit enter. And now we have a ball and stick model of ubiquitin. One of the things that we want to do, if we want to 3D print this entire ball and stick model of this protein, we're going to need some connectivity between these different pieces. And we can get that in the form of hydrogen bonds. So what we're going to go do here in this case is go to Tools and do Structural Analysis and find H-bond. Now for simplicity, to keep the number of hydrogen bonds down, I'm going to click off this Relax H-bond Constraints. And then I'm going to go ahead and click OK, and now you see we have a number of these blue hydrogen bonds that have been generated. Now at this point, they won't be exported as cylinders just yet. We need to do a couple of other modifications. In this case, we go to Tools, General Controls, and go to the Pseudo Bond panel. And here, if we highlight the hydrogen bonds, we can then configure the hydrogen bonds themselves. Oops, that's not the one that I wanted right there. Attributes, so I select hydrogen bonds, click attributes, and here we go to the component pseudo bond attributes, and we need to change this bond style here to be stick. And when we do that, we've now altered that to be sticks, and I'm going to increase the radius of this just a little bit, so 0.25 for the hydrogen bonds in this case. And now we're essentially ready to go. You could do things using UCSF Chimera by putting in extra hydrogen bonds or things like struts. This is also allowed in the pseudo bond panel, but some of those things are also available in Moldprint 3D. So now we're going to export this scene. So we'll click File, Export Scene, and this is going to be exported as an X3D file, which is essentially the same as a VRML file. And we'll call this 1UBQ. I already have one file there from a test. I'll overwrite that, and now we're ready to open this in Blender. Okay, once we get into Blender, the first thing we're going to do is import the VRML file. This is the 1UBQ X3D file in this case. You double click on this and it opens up, and you see it's not placed in the center in this case because the coordinates are elsewhere here, but there is our entire model. We'll just move it so that it's towards the center here, and we rotate around. And the first step we're going to do is we're going to have to clean the scene. Now keep in mind, because this is a much larger object, there are many more objects in the scene, all of the processes are going to take longer in Moldprint 3D. But I'll go ahead and click the scene here. One of the things that I'll demonstrate in this video is how we would use some of the additional features of Moldprint 3D to do automated selections for a big molecule like this. Now one of the first things that I'm going to do is I'm just going to click on one of these hydrogen bonds, and we're going to look at what the radius, and you'll see what this has done is it's made one big group. So at this point this would be a single group. And to see what the radius is of that, I recall what it was, but to show you where we can find this, if I push N in Blender and come down here to Properties, Here, for example, it tells me what this is a cylinder, and this is a radius, has a 0.250. So if I want to do automated selection of hydrogen bonds using the Select H Bonds button, I'll have to make sure that it's within the proper radius. And here, it's exactly 0.250. So what I want to do is I'm going to make this slightly different. I'll make it 0.251 so that everything below that value will be selected as a hydrogen bond. So now if I select H bonds, every single one of those hydrogen bonds has been selected as an object, and the corresponding atoms that are connected to it. That means that each of these hydrogen bonds will be printed independently in this group. Now let's say, for example, we want to split this up at every single amino acid. We can do that by using select C alpha. And now this is based again on these atom property preferences. We would have to set the carbon radius and the oxygen radius so that it would know where to split the molecule up. These are already set for the default in Chimera, so in this case we can just click select C alpha, and now every single amino acid in this protein, all 74 of them, are an independent object which will be pinned at, in this case, the C alpha here. So here's another C alpha which has been pinned, and another C alpha which we'll have a pin at. Now if we want to split this up into, oops, don't want to move that around. If we want to split this up, we simply go to the pin and join button. And in this case, because we would be building this large model, I'm actually going to decrease this. I'm going to put this pin size at 3. This keeps the smallest number of potential conformations that we can have for putting each model together, because we have lots of amino acids. And I'm also going to increase the size of the pins so they're just a little thicker. It makes it easier to put them together. And now I'll click pin and join, and this is going to take a little while. And roughly a minute and a half later, it's done pinning and joining. Now we need to orient these along the build plate so that we have them in reasonable orientations for printing, and we can simply click floor all. And now every molecule is aligned as best as possible, orthogonal to the z-axis. Now one of the things that you might want to do before you go through and do floor all would actually be to go through and change the name. So rename each of these objects with the amino acid number so you would know which amino acid you're printing when. And simply now click export all, and each amino acid now would be written to its own separate manifold STL file for 3D printing.